You've probably heard of protein as something you need to eat to be healthy or to grow big muscles. But did you know the human body is made up of trillions of tiny protein molecules? So small you can't even see them with a microscope. Scientists at New York University are working on ways to get these basic building blocks of the human body to do some superhuman things.
So everything that you have on your body is a protein, right? Your skin, your hair, anything that you see on the outside surface is protein.
And this is Carlo, one of her students working in the lab.
Proteins have different roles. For example, just like there are construction workers and businessmen and bankers, in the real world, there are different proteins to accomplish different things inside our bodies. We've taken it one step further and taken an engineering approach and seeing what proteins can really do for us beyond what nature thought of.
And this is where it gets really cool. These scientists are working to take the best qualities from various proteins and combining them to make a super protein. These super proteins could potentially be used by doctors to cure cancer or grow bone tissue. Wow, you're good.
Thanks.
So, how do we do this? How do we make a new protein that's never been thought of? Well, you're gonna need some supplies. First ingredient, bacteria. Don't worry, not all bacteria is bad or makes you sick. Some bacteria is good and useful. The bacteria to make this protein is natural. So instead of harsh chemicals, it's better for the environment and safer for the scientists that use them.
You can imagine that it's like a factory that's supposed to be making something. A lot like car workers in Michigan. They know that they're supposed to be making something, but they just haven't received the designs yet. That's where DNA comes into play.
DNA is a set of instructions in every cell of your body and in all living things. It has all the information needed to determine whether you'll be a tree, a grasshopper, or a human being. DNA is the blueprint needed to make up all those tiny proteins that make you.
We use DNA to tell these little microorganism factories how to make protein.
We take our DNA and take our little bacteria, we put them in a mixture, and we electrocute them essentially so that the bacteria gets this shock. And then what happens is on the surface of the bacteria, its pores become wider. So when the pores become wider, the DNA gets access through the bacteria so that it can go inside the bacteria. Bacteria now are very sad because they've been shocked. What we do is we add very rich nutrients so that the bacteria can be happy. And so we add that and we incubate them at a nice temperature where the bacteria are happiest.
The next step would be growing the cells that we've introduced the DNA to on a plate of gel nutrients.
And then we pick that single bacterial colony so that it can grow in kind of these large triangular shake flasks.
And as we feed them, they start to divide. 1 becomes 2, 2 become 4, divide by 2. That divides by 2. Within hours, you can have yourself billions of cells, starting from just a few of them.
The first non-happy condition was the electric shock to get the DNA in. But the second non-happy conditions for the bacteria is to actually add detergent. We're adding that soapy substance into our mixture with our bacteria so that essentially it explodes.
Their guts are all over the place, but really, we just want that nice gold nugget of protein that we've made inside that individual cell. So that's kind of the equivalent of blowing up the factory and trying to find out where the car is inside the factory.
So, now that they have a bunch of proteins, the real fun starts.
What we look for is how they start to assemble.
Self-assembly is a process where a group of proteins organize themselves. It'd be like if your room cleaned itself.
The benefit to using self-assembly is that you don't have to do invasive surgery. For example, you can envision having molecules, right, that you make that are proteins, put them in a solution, and then inject them into the site that you want to generate the tissue so that it can self-assemble, come together, and then form the tissue kind of in the body.
Much in the same way as a cheerleader pyramid is formed, we had the idea of maybe doing that inside the body and also forming cartilage.
Hey fellas, looks like we're repairing an elbow. All right, coach.
And so the male cheerleaders will line up on the bottom of the ground. The cartilage cells that come on and get attracted to the male cheerleaders that are the foundation.
Cheerleader men at the bottom would be our protein. Female cheerleaders would be the cartilage.
And so the women cheerleaders are coming on and building right on top of the structure itself. And ideally that's what we're interested in doing, and that would be kind of what we would make as our contribution to science.
CARTILAGE, cartilage, woo!
So right now, we're developing a potential drug delivery vehicle that's protein-based.
One of the problems with, for example, cancers and trying to treat cancers is that most drugs, if you take them, it goes through your entire body. And so it not only targets your cancer, but also targets your healthy cells. And that often causes a bad side effect. Our proteins can serve as a delivery agent. He can actually not only hold the pill, but actually travel to the site of the body where the disease resides. He knows where the cancer is because it's warmer than the rest of the cells.
I think it's warm in Sector B.
And so he'll be like, oh, I feel warmth, I'm gonna walk towards the warmth, and then say, oh, I found it.
I found it.
And drop the payload, the actual drug, so that the cancer cells get the drug.
Mission accomplished.
The thing that I love most about being a scientist is being able to think of something right in my head that's made out of proteins, and going from something as simple as that to making something like an organ or treating disorders like cancer.
Oh, that is so beautiful. I want to be a scientist.
Maybe I can self-assemble you a lab coat in a PhD.